In the last class, we had written down the final formula for string scattering amplitudes, and we looked at various. We were looking at various properties that this amplitude has. I was a bit sketchy in describing some of these properties, but okay. Actually, before we start, we need to do some evaluation kind of stuff. I mean, it's not the evaluation that's important; it's the getting you to work, do some work. So we could have one or both of these. We could have either a long assignment, okay, or we could have some sort of there's enough of you so that I don't think it's practical. Okay, how about suppose I produce some sort of assignment for you. This assignment will basically be problems from Kurczynski's book, okay, covering the first 6 chapters or so, and then you submit these assignments, and maybe 1 or 2 of the classes I can have some of you come up to the board and show me solutions. Does that sound reasonable? Okay, so by the end of this week or early next week, I'll send you a list of problems in the first 6 chapters. There will be 7, okay, maybe 30 for you guys to work out. Please. Yeah. I mean, I'll choose them and make sure they're not. You learn something by doing that. Right. And then we'll see how it works. But we'll also have a couple of sessions where we discuss some of these problems. Mainly you guys will discuss them. Okay. Just to make sure that you have a chance to look through your stuff. Okay. Fine. So we'll leave any filling out of details of the part I've already talked about in the last class to assignments of these sessions. There was one part that I didn't talk about at all, though, which was the BRST invariance of the element. So let me recall that. Suppose I take my vertex operators and I perform a BRST transformation on the vertex. Okay, so we had 2 kinds of structures. Right? Sorry, we had C times V, and we had the integrated vertex operators. Let's first look at C times V. Okay, so what I want is Q V R S T. Does everyone know what I'm doing? We have this scattering amplitude formula, and I'm trying to check that I get the same answer if I replace the vertex operators by a vertex operator plus a small BRST variation. Okay. Okay. So let's see. So
we got the formula for this 8-byte scattering amplitude.
Yes.
And we could see that there is a summation over all the possible topologies that can appear in the middle, starting from the sphere to torus and other, because we had some sum over the different moduli. Are these at the same order? Like, is there some sense in which you say that?
Okay, no, they're not. So let me take a 2 minutes to answer that question. It's an important question, I should have addressed. You see, we discussed that on the worksheet of the string, the action, for instance, was square root g del alpha x, del alpha x, mu. And now, something that you could have asked me is whether there's anything else we could have added to this action. We've already discussed the cosmological constant. We've already discussed that you can add the term plus a. Just a number. Okay? And in fact, you remember, if you took this action, thought of it with a cutoff, we had to add a cosmological action, a constant term, in order to cancel the constant contribution to the vacuum energy. Okay? And then we use that as a principle. We use that as the principle to fix finite particles. That is, we wanted the vacuum energy of the theory to just vanish as in infinite space. Okay? So conformal invariance of every quantity, including things like energies, vacuum energy, dictated that the cosmological constant term was something fixed, which in some, let's call it zero. What we mean, of course, is depending on the cutoff scheme. Okay? But was there anything else you could add to this section? Now, the problem with the cosmological constant is that it is dimension-full quantity. And this guy is 2-derivative. And that's good because it's d2 sigma. But the cosmological constant is 0-derivative. That was dimension-full of the worldsheet because it was d2 sigma. But you can ask, is there any other 2-derivative quantity you could add here? And of course there is, right? This whole theory is 2-dimensional gravity coupled to a scalar field. But where's the gravity action? Why don't we have that? If you think back to the earlier lectures in this course, we addressed this. We said that in 2 dimensions we don't have this. It's irrelevant whether we have this or not, because this is a total derivative. But now we've learned a little more about this total derivative. We've learned that the integral of this total derivative is an interesting quantity. Right up to some 4 pi, was it 1 by, so up to some, it was 4 pi times 2 minus 2. Okay? So of course if you add it here, it does nothing except give you a number. Okay? It does nothing except weight all path integrals with the same genus, with the same number, but weight path integrals with different genus with a different number. Okay? So let's suppose that we had this worldsheet action and we added this with some number, some constant, okay? Which I'm going to call phi. At the moment phi is just some constant. Okay? And this whole path integral e to the power minus this will be in addition weighted with e to the power minus phi, okay, into, ignoring all the 4 pi's, 2 minus 2. Okay? So, let's call this quantity 1 by g squared. Just this quantity, whatever it is. I'm not sure whether I want a plus or a minus. Yeah. So let's call this quantity e to the power minus g. Sorry, this e to the power minus phi. Let's call it 1 over g. 1 over g0. So this becomes 1 over g0 to the power 2 minus 2g, which is equal to g0 to the power 2g plus 2. So you see what this does is weight sphere graphs with a factor of 1 over g0 squared. With torus graphs with a factor of 1. Okay? And weights, let's say the genus 2 graph with a factor of g0 squared, and so on. Now that's sort of interesting because that's exactly what happens for a loop counting parameter in quantum field theory. Okay? Diagrams with different loop orders are weighted differently with a coupling constant. Okay? So you say that there is a possibility of adding into string theory a coupling constant. And in fact we see that the genus expansion is an expansion governed by a parameter, and the parameter is this coupling constant.
Why is G0 small?
Why is G0 small? No particular reason. But it's an arbitrary parameter. So if G0 is small, the genus expansion is a good expansion. Okay? If G0 is large on the other hand, String perturbation theory is useless. Just in the way that Feynman diagram perturbation theory in a field theory would be useless at strong coupling. I mean, you could still formally say that this is some graphs. Like here, you could say it's a sum of genuses. But if your answer is dominated by what's happening in a very large genus, what do you learn from it? Alright? Now, right. So, right. So string perturbation theory comes with an inbuilt perturbative parameter that is a parameter. Okay? That is not fixed by anything in the theory. As we continue our study of string perturbation theory and the structure of string theory, we will say that this parameter is in fact the expectation value at infinity of one of the fields of string theory, namely the dilator. The field whose vertex operator is okay, we'll see this. We'll have to do a little more study before we see it.
But how did we say this?
Well, we will see that this field phi, that this number phi, is related to the value of this field at infinity. Okay, this is going to be an interesting thing. You see, in quantum field theory, parameters are just parameters. In string perturbation theory, as we will see, I will have to show this to you, but see this. In string perturbation theory, as we will see, there are parameters, but the parameters are not numbers that can be added to the game. They're values of dynamical fields, basically expectation values of dynamical fields. Okay, so the fact that we had a parameter in the theory actually is a reflection of the fact that there is a flat potential in classical string theory for some field, and depending on so that becomes moduli space of vacuum. Okay, and depending on where we are in this moduli space of vacuum, string perturbation theory is a good expansion or a less good expansion. Okay, so string perturbation theory has an effective parameter, even though it won't turn out to be just a number you can add to. You know, if you were imagine doing string field theory, there's no number in the game that is undetermined in the string field theory Lagrange. What is undetermined is which vacuum you're working. Okay? Hang on a little bit before seeing that, but it was a good question.
You're saying that the phi here will get determined by the whatever modular parameter that I integrate over in the path integral.
The modular parameter. Say that again.
And we had some modular parameter which told me while we were integrating over
modular. I didn't understand.
The T parameter that told me about.
Oh, those are totally distinct. T is something about the world sheet. Okay? T is the set of metrics we have to integrate over. Okay? That is, a method of computation. Phi will be a field in space-time. Okay? In fact, will be the, for every, corresponding to every vertex operator on the world sheet, there is a field in space-time. Is this statement clear to everyone? The solutions of string theory. Do you remember? Go back to our first few lectures. We quantized the world sheet of the string, and what did we find? We found that the full quantization was given by the oscillators times 0 modes. Okay, and subject to a constraint that told us that the 0 modes await a particular wave equation depending on the mass, the energy of the oscillators. Okay? And that wave equation we interpreted as a Klein-Gordon equation. It's space-time. Right? So, for every oscillator state of the string, there was a Klein-Gordon field in space-time. field with different masses. Okay? So for each vertex, and remember the state operator corresponds. For each vertex operator on the string, for each state of the cylinder of the string, there is a field in space-time. More precisely, for each BRST cohomology class of vertex operators on the string, there is a field in space-time. Okay? And so for this, the operator in whose BRST cohomology representative is this one, some particular operator, some particular field in space-time. It's a scalar because of our factor away all indices. It's massless because this is dimension 1, so e to the pi kx may have dimension 0, this is what I have to 1, 1. Is this clear? Okay, so this is a massless state. It's a massless scalar field. This massless scalar field has a name. It's called the dilaton. And I'm claiming that it's the value of this dilaton at infinity. I'm just bringing the expectation value background of it, which is starting, is the effective looped up parameter. The effective thing that it is. Is the claim clear? We'll see it as we go.
One small question from last class. So we had this while anomaly sort of way for proving the Riemann last year. It was a bit confusing to some of that because we had this conserved current corresponding to the global symmetry, and we extensively used the conserved charge in proving the BRST cohomology system.
Right.
But now it seems that on general curved world sheets, divergence of J does not vanish. So it means that there is no conserved charge in.
It's true that there is no conserved charge anymore, and you say, but then how is that consistent with the fact that we used ghost number conservation? How is that consistent with the fact that we used ghost number conservation so heavily in our BRST? But we were not using any dynamical conservation. See, the whole discussion of the BRST cohomology, in our discussion of BRST cohomology, we were just producing, we had an operator which carried a certain ghost number. And then we used the fact that the inner product between two operators, two states, okay, had to be 0 unless those states carried equal ghost number. Okay? This is not a statement about dynamics, it's a statement about kinetics. Let me explain that one. See, there are two things that you might want to say. One thing that you might want to say is that psi f prime psi I, okay, with insertions including time evolution, can only be non-zero if the two guys carry equal charge under some charge, and that is only true if the charge is a conserved charge. Because you have to take, what's the argument? The argument is you take your Q, your charge wherever it is. Q ghost. You act on this, you get some number. Then you take it through all the operator insertions and through the time evolution. Okay, and then you act on this. You pick up some numbers as you go through the operator insertions. You pick up nothing as you go through the time evolution, commutes with the Hamiltonian. Then you act on this. So that will tell you that this whole matrix element can only be non-zero if the sum of this plus insertions is equal to this charge. That requires dynamics. It requires conservation because it requires you to be able to take the charge through the time evolution. But suppose we just do kinematics. We're looking at inner products of states, or inner products of states perhaps with some operator insertions, but with no e to the power h. Okay? Then the statement that any two states have non-zero overlap only if they have equal host number, okay, makes no reference to dynamics. Okay, so as long as the inner product is suitably defined, it's defined so that this host charge is a Hermitian operator. Right? This is just true. That's the only kind of statement we used. You could have thought, as far as the BRST discussion we used, host number can be thought as a bookkeeping device. You see, the whole discussion had no dynamics in it. It was just a statement about a particular operator and its cohomology. That operator had a certain commutator with the BRST charge. That was just true. And that's all we used about it. Do you understand? Okay? Good. Good. Any other questions?
So somehow I thought we were using that del dot j was conserved because we related the value of del dot j to the number of B and C insertions, right? And that's something you do for conserved currents.
Okay. Now, we related the number. In yesterday's, in the last class.
Yeah.
So in the last class, we actually showed that del dot j was not quite zero, right?
Yes. And then we related that to the number of B and C insertions.
B and C insertions, right. So I think what I interpret Ashish's question was as follows. In the last class, we actually showed that the host number was not exactly conserved. And we determined that the extent of non-conservation of the host number to the genus by the Riemann-Roch theorem, and then related that to the number of B and C zero modes, also therefore to the number of B and C insertions in order to get a non-zero result. That was one possibility, and this is true. But I thought what made him uncomfortable was that we previously used the same host current, the same host charge, in a discussion of BRST cohomology. And he was saying, well, doesn't the fact that you've shown that it's actually not quite conserved invalidate your earlier discussion of BRST cohomology? I'm saying the two are logically independent things. Is this clear?
What makes me uncomfortable is like different thing.
Yes.
The point is when we related the value of del dot j to the number of B and C insertions.
Yeah.
Doesn't this statement itself assume that G is conserved? Because you generally have that.
Let's go through that discussion. Okay. So we went through this very rapidly last class. I will more carefully. Okay. Well, but if you're confused, it's likely. It's good. Let's do it. Okay. Okay. So let's start. Let's start with our general discussion of the Noether theorem. So suppose you've got an action d5. I won't try dpdc all the time. Something. Okay. And v power minus s. And you remember that our general discussion of the Noether theorem started this way. Is that suppose I take the change of variables phi is equal to phi prime plus epsilon of phi prime. Epsilon is something very small. Or maybe epsilon times some g of phi prime. But epsilon is very small. Then you plug this change of variables back into this integral. When this, in general, what will be it? We are going at d phi prime e to the power minus s of phi prime. Just because epsilon is smaller, so leading order will get the same thing. But in general, what we would get is epsilon times some h of phi. There will be some first order change in the integrand for an arbitrary variable change. This is what in general would happen. Okay? What we had said is that the cases where this change of variables does not result in an epsilon times h of phi prime. Okay? Those changes of variables are symmetries. Okay? And then, so we said h of phi prime equals 0 is symmetry. Then we went on to show that for symmetries, we associated with symmetry, we always have a conserved current. Remember how we went on to show this? We said now, let me make the same change of variables, but instead make epsilon a function of position on the worldsheet. Okay? So, for the general case, what would we get? We get this plus del mu epsilon, maybe it's called del alpha, epsilon times j alpha. Whatever you would have got when epsilon was a constant plus something that depends on the derivative of epsilon. If it depended on two derivatives, we integrate by parts. You can always write it this way. Right? This is true in the general case. Now, z was equal to this, z was also equal to this. The path integral hasn't changed because it's just a change of variables. Now, let's go back to the general case. The general case, because these two path integrals are the same, their difference is 0. To get the difference, I just expand out these exponentials in epsilon. So what do I get? I get the statement that after integration by parts, I'm doing it schematically after sign. I get integral epsilon times del dot j del dot j plus h is equal to 0. Okay? And then we had a more careful discussion including also other operator insertions, which is not going to be of relevance to me here. So this is the general case, and since epsilon was arbitrary, then we remove this integral sign and so on. Well, you get the operator equation del dot j plus h is equal to 0. Okay? Now, in our discussion at the beginning of this course, we didn't have this h at all because we assumed that epsilon that this was a symmetry. And therefore we got the equation del dot j is equal to 0. Okay? But suppose we've got something that is not a symmetry. Okay? Then we're going to get an equation like del dot j is equal to h. Okay? Now, so what we're going to do is to now relate. Okay? What we're going to do is to relate this h here to the number of b minus c, to the number of b minus c insertions. Okay? How is that h related to the number of b minus c insertions? This is related from just the question about whether a path integral is 0 or not. Okay? Suppose I've got some path integral which is d phi, and then you got some operator insertions. Okay, now I'm switching to b and c. So I've got some number of b insertions, some number of c insertions. Okay? And I've got my e to the power minus s. Now I do this purported symmetry transformation on that path integral. Okay? Now the symmetry transformation changes, and I do it for the constant value. Okay? So I do it for epsilon equals constant. So that symmetry transformation phases B in a certain way, phases C in a certain way, but also picks up something from that action. Okay? Now, because a change of variables cannot change a path integral, if the path integral is non-zero, the total phase factor that you pick up must vanish. This is clear? Okay? So the phase factor that you get because of phasing B plus the phase times the phase factor that you get by phasing C times the phase factor that you get from the e to the power action. Why do you get a phase factor from the e to the power action? It's because the action has changed. So you get a new term which is this integral of h. Okay? But what was h? H was del dot j. So you get integral of del dot j. Okay? So you find that the number of B insertions, so let's say that C picks up phase 1, B picks up phase minus 1, number of C insertions minus number of B insertions plus phase that you get, plus the phase that comes from integral del dot j with a suitable normalization must add up to 0 if your amplitude has to be non-zero. Of course, if your amplitude is 0, you don't need to get the same phase because 0 times any phase is 0. Is this clear? Okay? So, the relationship between the number of B insertions minus the number of C insertions and the integral of del dot j follows from this logic. Is this clear? Okay? Where did del dot j come in? It came in, actually it's the integral of whatever you get from the change of phi when you do this check. But we see that that is related to del dot j. Yeah. So, let me say this again. If you have a symmetry, it typically happens when you've got something that's a symmetry of the classical action. And then you find that it's actually not a symmetry of your quantum action. What does that tell you? What it's telling you is that when you perform the variable change, the action is not staying in there. And del dot j is measuring the extent to which it's not staying invariant. Okay? And that extent to which it's not staying integrated is related to number of B minus number of C. Is this clear? Okay, any other questions?
We never worry about the boundary conditions of the path integral.
We never worry about boundary conditions of path integrals when we do such things. You're saying even though this is a constant, you don't worry about that. We would have to think about it. The point is that in Euclidean space, these path integrals decay in very rapidly, extreme corners of configuration space. That's the point of going to Euclidean space, right? E to the power minus del phi square. Either phi fluctuates very fast. Anything it does anything violent decays rapidly. That's the general philosophy. Now, that in any particular case, you should carefully justify it. Okay. Sorry, Peter.
So you get a relation of number of B minus number of this sort of term.
Why B minus C? It's because C had charge 1 and B had charge minus 2. So when you do this variable change, each of these insertions picks up a phase, B insertions pick up minus that phase. And then the measure picks up some phase. The whole thing has to vanish. Okay? And any other questions or comments?
One last thing.
Go on.
UTR is one term that you add. There are other Lorentz invariant terms, but that you cannot add because that would introduce other dimension, full dimension.
Exactly. You see, it's the general story of quantum field theory. In a quantum field theory, you can always add lots of terms to your Lagrange. Most of these terms are irrelevant. Okay? So there are sometimes some terms that are relevant. The cosmological constant term was relevant. It had an effect, but we had a principle for determining its finite part. Okay? The irrelevant terms are just irrelevant and continue, just as continuum quantum field theory. They just come out there. Yeah, they appear, their effects are suppressed by 1 over the context. You remember our long discussions on renormalization? Okay. Excellent. Other questions?
Is there a theorem saying that in what cases can you go from enclosed K to the Euclidean?
That's a very good question. It's a very confusing topic. In what cases can you analytically continue, right? Well, there are some examples where the analytic continuation is very fishy. I don't know any theorems, firstly. They probably exist, I don't know. Other theorems guaranteeing analytic continuation. Okay. See, where it's particularly fishy is if you perform the analytic continuation and you find something a little strange. Okay? So there's a nice example of that, which is gravity. Have any of you ever encountered this? You know, if you take Einstein gravity, which is in Minkowski space, and then you analytically continue it, you get Euclidean Einstein gravity. Okay? Now, Euclidean Einstein gravity has a particular pathology. That is, the action, Euclidean Einstein action, is not positive definite. Because of the wrong sign of the kinetic term for the conformal. If you take a metric, okay, and you freeze it to be of a form, some particular metric you have, maybe eta, times e to the power chi. As you just look at this particular class of metrics and plug it into Einstein's action, and ask what effective action does it induce on the field time. It induces an action that includes a term this, but if you stare carefully at this term, it turns out to be a term with the wrong sign. Okay, the wrong sign, even in Euclidean space. So, if you really want to be the Euclidean path integral here, this path integral looks like it makes no sense. It looks like it gives you a diagonal. So, I think that analytic continuation of an Einstein, of the Minkowski space path integral to Euclidean space, though we often do it, people have prescriptions for how to deal with this problem. But that's like this is a clean indication that something's going on. I think, typically speaking, if you do this analytic continuation and it works out, that is, typically speaking, an analytic continuation is okay, provided nothing's blowing up at infinity or something like that.
Is it problem specific or dimension specific?
It's both. No, I mean, what do you mean problem specific?
Suppose that given, say, some dimension, say 4D, given a certain set of problems where there is no problem.
Problem meaning Lagrangians or processes?
Say Lagrangian.
Lagrangians, yes, it could be Lagrangians.
But in certain cases, you can definitely say that you can continue.
Yes, for instance, for quantum mechanics. Now, you can easily prove. You take quantum mechanics, discretize it. Okay? Then that you can, at least if you allow me to discretize it. Okay? Yeah. For many cases, you can, at a certain level of, let's say if you allow me to discretize and put it on a compact time, then I think you can clearly prove just some analytic continuation of a finite path. Okay? And with where the integral has good properties. Decays at infinity. Yeah, so there you can clearly. But you will have to look at it case by case. But
No, I was asking like, suppose, can you say for certain, say, less than some D dimension that for every Lagrange that you can write with?
I don't think so. Well, the Lagrange may have some properties. I don't think there's something very different. Okay, other questions, comments? Okay. Fine. So let's get back to our. Right. So what we were trying to do was to check that the path integral that computed our S matrices was BRST invariant. Okay. So we had some insertions, and so we had dx, db, dc, e to the power minus sb, s ghost minus s matter. Then we had insertions, this b, del k, g insertions. We had some fixed vertex operators, and then we had some integrated vertex operators. Okay, and the schematic. This is the structure of the path integral that computed string S matrices. Okay, and of course we have the integral over coordinates. Now, I want to check that this whole path integral is BRST invariant. As I do a BRST transformation on this integral, I get the same answer. The BRST transformation is symmetric. Otherwise, all hell will break across. Okay. Now, we've already checked that this local part is BRST invariant. That's just a statement that the BRST current is a good current, it's 100% conserved, so all those things we checked, and D equals 26. This you remember from last time. So the only issue is with these insertions. Only potential issues with the insertions. Okay? Are the insertions all related? Okay? So, are the insertions all BRST invariant? Well, let's look at the insertions one by one. Let's first look at C times B. Okay? Now, in order to find the commutator with the BRST operator, what do we need to do? What's a good way of doing it? Or B with J. So what we want is C times D plus the other stuff. Let's call it J BRST times C. Z times this setup. Okay. Now, let's look at what we get. JBRST includes let's look at what we get when we have something acting on V. That can only come from the stress tensor part of JBRST. Okay. So that what's the structure of that? That's C of Z, D of Z, C of W, V of W. All right. Let's take the hit this with this. Now we know that V is a dimension 1, primary operator. So we know everything about the singularity of this with this. Okay. So that's C of Z, C of W. Times 1V, V of W by Z minus W square plus del V over Z minus W. This here. Okay, so if we want the pole, what we have to expand this guy. So that's del C of W, C of W V of W plus this term here just gives us C because we just have to set C equals W, the Z equals W, okay, and if we set Z equals W, we just get C squared. So this is the thing we get. Okay, so KVRSTZ acting on C times V. The part that comes from the matter stress tensor, actually we don't need. Sorry, let me not even go through. This is a subset of what we did in our BRST quantization. All I'm going to show is that this thing is a BRST invariant operator. But we already went through that. You remember our demonstration that this was an element of BRST cohomology? Okay, I'm just repeating that here. Let me not go through that. Okay, so the fact that C times V was an element of BRST cohomology, in particular meant that C times V was BRST closed, and this is something we've checked in great detail 3-4 lectures ago. Okay, I won't go through that. I will walk through that too badly. Okay, so fine. So these, okay. So these insertions, BRST closed, no problem. Okay? Now, what about these insertions? What about insertions of integral of V? Insertions of integral of V are more interesting because they are not by themselves BRST. V is not by itself BRST closed. Okay? So let's look at insertions of integral of V. Insertions of integral of V, now we have to go through this procedure for that. And basically the algebra I went through here, except that there is no CW. Okay? So it's the same thing, but we would have got C of Z times V of W by Z minus W, the whole thing squared, plus del V of W by Z minus W. This clear?
What will take
the OP of JBRST with V of Z. V of Z, V of W.
For the last part, integral, which operator is trying to show you which part of the insertion?
I'm looking at this. Yes. Is this clear? Sorry, we just went through the algebra. Right? Because JBRST is C times T. V has non-zero in it. There's no singularity with C, so it's purely with T. You just take C of Z times the T VOP. T VOP was this, and then I multiply the C. That's clear, right? Everyone? Okay, excellent. So, now we have to data expand this term. This term remains. So you see that the net pole is del of C because it's del C times V plus C times del V. Right? Because here I need to get a pole, so I have to Taylor expand this. So I get del C times V. Here it's already a pole, so I just set C equals, so that's del V. So it's del of CV. Now that is the VRS, the change in VRS. Okay. But remember that V appear integrated. Okay? So this is under the integral side. Okay? So provided that the integration has no funny terms when this guy hits some other operator, provided that the integration region is good, nothing funny happens at boundaries. Okay, which actually was what Ashok's talk was all about 2-3 weeks ago. Okay, understanding, the collinear. Okay, provided there are no funny things associated with boundaries. Okay, this is embedded. Okay, actually ensuring that there are no funny things occurring at boundaries and doing that in a clean way is much harder. Though it's true. It's true to the extent that we understand it. Okay? Well, this is the basic mechanism. That the change of this here, it's not BRFT invariant, but it's variation under BRFT transformation. It's a total derivative. And you're integrating a total derivative. Okay, and so you should get 0, provided there are no such things. Okay? What remains is this guy. Go on.
But you still have a CV term, right? Like
CV was by itself BRST invariant.
no, in this JVOP, you still have a CWVW term.
We have not with a pole. You have CWVW by Z minus W, the whole thing square. But we're not interested in the OP, we're only interested in the commutator of BRST. We're interested in the residue of the pole. Clear? Okay? So, dealing with possible subtleties when things hit each other and so on, that is, we'll do more carefully as we go. If these are examples, you'll see better how this works. But the basic idea is that this is a total derivative. Yes. Okay. What remains here is this B del kg. Okay. So now, what is the change in B del kg? Does anyone remember what the operator product expansion was between J BRST and B? Of course, the operator product between J BRST and del kg is 0 because G is a number. What's the BRST? What was the pole BRST current with B? Do you remember how we started up? It played a key role in our analysis of BRST pole. What? JB of Z with B of W. What was the pole?
Minus BW.
BW. T by Z. You remember we used this plus the fact that B0 annihilated the vacuum meant that T annihilated the vacuum. And then this allowed us to consider to look at cohomology on a smaller space, the space of things annihilated by this. By T0. So. Okay, anyway, so this is how this goes. So, if you look at how this, the variation of this under a BRST transformation, B changes to the T, so you get integ T del kg. Okay, that's the BRST variation of that. That's also not apparently invariant. What's T? T is the change of the path integral because of an infinitesimal change of the metric. Okay? And what was this? It was an infinitesimal. This was the infinitesimal change of the metric caused by a variation of modulus. So what is this net insertion? Under the infinite, it's d by dk. Okay, so t was equal to del log z by del g. Okay, but so t times so t times del g del kg This is clear? It's the change in the path integral. Okay? Because when you change the modulus a little bit. But remember that our formula had a d kt. And the moduli space over which we will always be doing our path integral. It's always compact moduli space. We'll see examples of this as we go. So once again, there's this argument that we're doing, integrating a total derivative over a compact space. So you can see. Okay? So, you see, even though the insertions that we have put into our path integral, out of the three kinds of insertions, only one of which is explicitly BRST. This was very nice because it was what appeared in our BRST cohomology discussion. The other two insertions didn't look BRST invariant at all. Yet they did not produce BRST variations in the full path integral. Always by the same logic. That you're doing integrals of total derivatives. Now, this was another element that entered Ashok's talk 2 or 3 weeks ago. Okay? Once again, the argument that the integral over total derivative is 0 has what? Potential subtleties. If these potential subtleties are related from one way of looking at them to infrared divergences. Okay, that could invalidate the argument. Okay, and it's essential to prove the unitarity of string theory. BRST invariance is essential for unitarity of string theory. And so to carefully check real unitarity, you need to carefully deal with every potential source of subtlety, as Ashok was doing so fantastically painstakingly in this talk. We will see some of the potential problems, but once we will not attempt to be that. Okay? But these are the naive arguments that everything is good. And then, to be really careful, you have to chase them down. Any possible place that basically in all of these arguments, the potential problem is that you say, I've got a total integral of total derivative at 0. And then you have to be very careful that that is indeed true. Okay? Those are the places where things can go problematic. Okay, fine. Okay, so, but our level of care, okay, we've established BRST invariance of the S matrix, and of course, it's not because it's as simple as this. All I'm doing is giving you formal analysis, but people use actually calculations. If you have a problem, you see it. So at least if you had a problem up to, let's say, 2 loop order, you would see. And you don't. There's sometime when I was a postdoc, there was this complete computation of a 2-loop scattering amplitude in this RNS formalism by but totally explicit, everything done very nicely, no problems. Of course, it would be nice to have a real proper proof. There are no order in the genus expansion. Do we get trouble? And that's the kind of thing Ashok is after, right? And since he's after it, he'll do it. but every indication is that things are not. Okay, fine. So now, one of the things I'm going to encourage you to do is the following. I'm going to encourage you people to look at the string scattering formula and to ask every question about it that you can. How do I know that the answer doesn't depend on which vertex operators I fix and which I don't? How do I know that it doesn't depend on where I fix the vertex operators? Okay? Ask these questions, try and answer them. We've addressed several of these questions. We haven't addressed all of them. Ask every question you can about the sensible nature that guarantees that this is a sensible answer. Try to answer it, and if there is any question you cannot answer, you bring it to me. I will try to answer it. Okay? This string scattering amplitude is one of the most important formulas, one of the most important formal formulas in the class, and you should try to understand it as thoroughly as you can. Okay? Excellent. But we'll declare victory for the purposes of this class. It's 1:30 already. And okay? Excellent. So now that we've developed some momentum with studying string scattering, and it's great to have a formal formula, but we need to do some calculations. Okay? So now that's where we're going. We're going to actually start calculating some string scattering amplitudes. Now, in order to do that, I need to set up a little machine arrays so that help you to quickly compute expectation values of vertex operators. Okay? So, let's start with that. Suppose I was interested. So, you see, the kind of things that we need to compute are expectation values of vertex operators with some B insertions, some C insertions, and some matter insertions. Our first few calculations will all be on this sphere. How many B insertions will we have on the sphere? 0. So let B be right. Okay. How many C insertions will we have in the sphere? 3. Excellent. So let's deal with the C insertions first. Okay. So what I'm going to ask is the following. I have C of Z1, C of Z2, C of Z3. Similar insertions of C bar. So we'll let that wait. Okay? And I want to know what the answer to this to this expectation value is. Okay. Now, actually, I can say in more generality. Maybe I'll work it out in more generality. First, let's look at this guy. What can we say about this guy? First, on general grounds. C had dimension -1. So the answer should scale under scaling like Z to the power +3. Yeah, Z is dimension -1. Okay? Great. So the whole thing should scale like Z cubed. Okay? I'm not saying which Z. Then, what else can we say about this? What are the symmetry properties? If we interchange Z1 and Z2, how should the answer change?
Minus.
By a minus sign. Because if I made this Z1 and this Z2 by flipping these two, I go back to the same one, that makes up a minus sign. So should be odd on the interchange of Z1 and Z2, odd under the interchange of Z2 and Z3, odd under the interchange of Z3 and Z1. Excellent. So that tells you. Oh, and by the way, of course we could have. Great. So we got some information. And can you tell me about the singularity structure of this? Whenever they coincide, and what is the singularity when they coincide? No singularity. Entirely regular function. Okay? So we've got a nice, beautiful regular function. Therefore, what do you know about regular functions that are analytic? Yeah.
Power series.
Power series, yes. Power series that grows like Z cube, which therefore is a polynomial. It's a degree 3 polynomial. So we've got some degree 3 polynomials of Z1, Z2, Z3. Okay? That what must happen when Z1 and Z2 coincide? 0. What power is that 0? Is it like Z1 minus Z2 to the power 1, or to the power 2, or to the power 3? To the power 1. Because you can work on the OP. It's
1 by 6.
del CC is not 0. So it's the first Taylor expansion. Okay, so what can the answer be? Z1 minus Z2 has to have a 0 and Z1 minus Z2 when the 1 hits 2, has to have a 0 when 1 hits 3. It has to have a 0 when 2 hits 3. And then it's some function of Z1 minus Z of the Z's multiplying this. What can that function be? It's constant. Because we've already got a degree 3 polynomial. So this is the answer up to now. Okay? So, in fact, we can easily work out even this number by just looking at the by looking at OPs. But I won't even bother to do that. Okay, so up to some number, I think now but anyway, up to some number, the product of the insertion of three C's, C1, C2, C3, is just this. So you see, we could have tried to work this out by working out a determinant, or looking at the path integral or something like that. So in this case, it was so easy we didn't even need to look at it. Okay, so just as a little quick intellectual exercise that will be of use only when we get to computing genus 2 amplitudes. Just joking. Yeah. Okay. But suppose we had a bunch of C insertions and B insertions. Oh, first let me try. Suppose we had just some B insertions. But that's not. Yeah. So suppose we want the sphere. We know the number of C's by the number of B's has to be 3. So we won't try to violate that rule. So suppose I had C, 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 and there are n plus 8. And we have B, 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 and M of those. And I'm trying to and these were, let's say, at Z1 up to Zm plus 3, and these were W1 up to W. And I try to compute the expectation that this correlator of these guys. Let's say what we can say are general parameters. Okay, so now we are experienced with these kind of arguments. So what can we say? Firstly, this is some function. What are all its singularities? Singularities occur when
0 and W.
When some Z hits some W. Any Z hitting a W is a singularity. What is the nature of the singularity? Simple pole. So there must be a denominator which is of the form product I is equal to 1 to m plus 3, product j is equal to 1 to m, zi minus w. There must be a pole. This must be there. Now, what can we say about the zeros of this function? What can you say what happens when one of the z's hits another z or whatever? What?
You contracted m plus 3 c's with n b's.
Sorry?
You contracted m plus 3 c's with n b's.
No, but I'm not saying that I'm doing a particular contraction. I just know that if any of these z's hits any of the w's, there's a pole. Okay, so I'm going to write down an answer. I'm going to try to write down a function that has this property.
Sum over by
So let's say we got sum, and then each of the sum has this pole, and then I'll factor, make the denominator common.
Oh, you put stuff on top.
I'll put lots is coming.
Okay.
Yes. This is just the most general answer that has a pole everywhere that it has to.
Also, on calculation of the sphere, such a term will never come, right?
It will never come because we never have these. No, that's why this is a pure theorist's flight to fancy. Okay, just because it's possible, because it's so easy to do these calculations. I just want to show you that. Okay. Okay.
Also, are we looking at this formal correlation, or do we expect the V path integral to factor out something?
You see, because the action is a sum of action for BC and a sum of action for matter, we do the correlations piece by piece. Okay? Good. So, good. Now, what do you say about when two z's hit each other? We must have zeros. So, there must be a factor product I is equal to 1 to n plus 3, product j is equal to 1 to n plus 3 of zi minus zj. And similarly, there must be a product when two c's hit each other. Same thing, you get zeros. Is this clear? Okay, so product I is equal to 1 to m, product j is equal to 1 to m, zi minus omega wi minus wj. All these terms must be there, but now this totally exhausts the zeros and the poles. Which means that whatever this function multiplies, that function and its inverse are both analytic functions. Okay? So, there are not too many options for what that can be. Because it's an analytic function, it has to be a polynomial, it has to be a polynomial also 1 by z. It's the inverse also. Okay? So it's basically a constant. But let's check now, all these arguments are very slick. But if we got the argument right, there's a check. Dimension shared. Okay. So let's see. What are the dimensions of C? That's -1. Okay. What are the dimensions of B? That's 2. Okay. So the total dimension here. The total dimension here should be 2 into m minus m plus 3. Correct? That should be the total dimension. So that is equal to m minus 3. So the net homogeneity in Z should be 3 minus m should be the homogeneity in Z. Okay, let's check with that. Yes. Okay, is this the right homogeneity? Let's check. In order to see whether this is the right homogeneity or not, we just count. So this guy, how many were there? Well, all we have to be careful about is that this term did not include I equals j. Because of course, there's no singularity when I when two guys hit each other. Okay? And it's a pairwise thing. There's one product like this for each pair. Okay? Sorry, I didn't. Okay, it's product over pairs. Okay? So, how many of these terms are there? The number of elements in an antisymmetric m by 3 times m by 3 matrix. Okay? So that's m plus 3 into m plus 2 by 2. How many of these guys are there? That's plus m into m minus 1 by 2. Now how many of these guys are here? Here there is no slam about equal guys and two antisymmetries. They're different things. It's just product. Minus m plus 3 into m. Okay. Okay? So this is equal to half of m plus 3 into m plus 2 plus m into m minus 1 minus 2 m plus 3 into m. Okay. Okay. And now we have to compute this. So firstly, this is m square minus 2m square. So m square is cancelled. So it's going to be only linear terms and the constant term. Let's look at the constant term. Constant term was 6. That's just 6 by 2. So constant term is 3. Okay? You get the minus m as well? Yeah. Let me just check that also. So that's 5m minus m, so that's 4m
minus 6 by 2.
4m minus 6m. Yes, minus 6m. Minus 6m by 2. Okay, homogeneity works out right as well. Okay, so who can doubt that our slick argument is correct? Okay. So this only works occasionally, okay? But when it works, it's so beautiful. We've computed an infinite number of correlation functions of the BC system in one shot. It's really quite cool. Okay. Okay, great.
So, as lay calculation would not give you anything looking similar to this. Because suppose I just start doing CV guys, I get some m z minus w's on the bottom, and then I do one CC, I get one z minus z on top, and then I have C left alone.
You will
like each of it will be a bunch of terms like this, but I'm going to have a C left alone.
You see, what's going on here is the zero motion. You see, what's going on here is the fact that 3 C's with a sphere. So you could have asked that question just about C's. Okay? So what's going on here is the fact that 3 C's of the sphere are not zero as you would naively have thought. Because you have to absorb the 3, zero modes of the path integral. Okay? After that, it's what you're saying. 3 of the C's are absorbed by the zero mode part of the path integral. And then the rest is what you're saying. Now to do that zero mode carefully, we would have really had to, be on the sphere. Okay, actually, yeah, we could try that as well. It's that determinant formula. Okay? But yeah. But even so, that would actually have given us the same answer pretty fast. Let me give you the same answer for 3 C's first. Do you remember we had a formula for it last class? We said that the 3 C's was just the determinant of. Come, nobody remembers this? We had C's and Z's at Z1, Z2, Z3. Do you remember what we said was that as far as the C insertions are concerned, only the zero mode matters. So we can replace C by just the expansion in terms of zero modes. Okay? And then we get a determinant of C0I Zj. Zj's are the 3 positions. C0I are the 3 zero modes. 3 zero mode functions. Now in the last class or previous class, I don't remember, in response to another class question, we also worked out the 3 zero modes. Can somebody tell me about that? 1, Z and Z squared. So let's compute. This is the determinant of 1, Z1, Z1 squared. 1, Z2, Z2 squared. 1, Z3, Z3 squared. Okay, can somebody tell me what this determinant is? It's this. Why do we know that? We know that it's 0 if any of the Z1s are equal to Z2. That has to have this factor. We know that it's maximum, any product, one cubic. So it has this factor, it's this times the number. Okay? So you see, an honest calculation has to carefully take into account the zero modes. Okay? So, an honest calculation will go along these lines, or even more honest, really put the metric for sphere. But then the other thing would have been much more difficult. Because you see, 3 of the C's would be absorbed by 0. The rest would have contracted. Then you'd have sum over all choices. You would have got a lot of combinations. Then you would put them all together and finally miraculously found this. But it's not no, the answer. Okay? Okay, great. So, we declared victory on computing BC correlation functions of the sphere. It was very easy. And we'll move on. Okay. Fine. Now let's move on to computing matter correlation functions. Okay. So, the matter correlation functions are, the matter correlators are also very easy. In order to start to touch upon this topic, we won't get to the end of it today. I'm sorry about this. Today's talk really ate up 1 hour of our class. But anyway, fine. Yeah. So, in order to do this, I'm going to remind you of a general thing. See, first, this is a general property of Gaussian path integrals. I'm going to remind you of. The general property of Gaussian path integrals I'm going to remind you of first by telling you about it in a simple context. Is the following. Suppose I have e to the power minus 1 by 2 alpha squared x minus a whole x squared. Okay? And type f of x. Suppose I want to compute this quantity. Well, I have some function. Let's say it's a polynomial function. Doesn't matter. But let's say it's polynomial. Okay. Now, you see, an easy way to compute this is the following. This is integral e to the power minus 1 by 2 alpha squared x prime squared by change of variables times f of x prime plus a of x. Okay. Now the point is that x prime can be computed. X prime now obeys Wick's theorem. We compute all insertions of x prime by Wick's theorem, by summing over contractions. Okay? That would not have been the case here. We could have computed the insertions of x by Wick's theorem. Because in addition to what you get from contractions, you get something from the value of x at the settlement. Okay? What you get is x, f, evaluated on the saddle point, plus a fluctuation field. So and then you have to do sum over all contractions of the fluctuation field. This is clear? Now I'm going to generalize this to a general rule, and you see if you understand. The general rule is that suppose you want to compute the expectation value of something inside a Gaussian path integral. The first thing what you have to do is to take the variable of that something and replace it by the saddle point value plus a formal fluctuation field, and then evaluate all contractions of that formal fluctuation field using Wick's theorem. It may not actually be though I've done this by change of variables, I could have said this here. I replace x by its saddle point value, which is a, plus a formal fluctuation field, and I contract that formal fluctuation field according to Wick's theorem governed by the standard deviation of x. Is this clear? Okay, so the shift in a Gaussian path integral, okay, is trivial as far as the integral is concerned, but it's not entirely trivial for insertions. And it's an obvious statement, okay, but it's an obvious statement that you have to, be careful, use properly. Now, why did I say all this? I said all this because the kind of insertions that we will be interested in are insertions of vertex operators. What are the kinds of insertions of vertex operators? Our vertex operators will always carry some momentum. So they will always have this structure. So we got some product AI, Xi of let's say Zi. But some of these vertex operators may also have dressings with things like del x, del by x. Right? So we could have del x, del by x associated with some of these guys. Now our action was e to the power I del x the whole thing square. And what having this does is like one of these terms. It's like taking e to the power minus x squared, that's the action, and putting a plus jx, which shifts the saddle point of the Gaussian integral. Okay? Stuff in the exponential changes the Gaussian saddle point. Stuff downstairs is like the f. Is this clear? Okay? So what I'm now going to try to do is to use this general rule to evaluate the correlation functions of insertions of this sort. Okay. So the first thing we have to do is to evaluate the saddle point. Okay. The saddle point is insensitive to all these insertions. So first let us look at e to the power I, ki, I, okay, let's say product I is equal to 1 to n. Let's look at computing this, and in the process of computing it, I'll also compute the saddle point of the saddle point of the downstream path. Okay, so you see, what was our action? Our action was 1 over 4 pi alpha prime del square del x. And then in addition, we have now an effective plus I ki x sigma I. So what's the equation of motion that we get from this combined this stuff with this added to the action? The equation of motion is, it varies, 1 by 2 pi alpha prime half del square x plus I ki delta of sigma I. I'm finding the equation of motion because I want the saddle point of my Gaussian path. This is clear, right? Okay. What's the solution to this equation of motion? Well, del square times source, del square on x is equal to source. You know the answer is given by Green's function. Right? Okay, so what do we have? We have that x is equal to the Green's function. It's a linear operator, so it's just the Green's function of each source individually. Okay, so is equal to